In our fourth and final portion of our engineering portfolio, we're focusing on vectors. And vectors pretty much are what we just did, in a sense, in our last part of our portfolio, where we talked more about like a robotics arm and moving to specific positions along the way. Well, that's kind of what we're going to be doing right here with vectors. And vectors are so important, especially when y'all get to statics and dynamics. When y'all get to that class in engineering, you're going to be doing a lot of vectors and breaking down vectors into their components. So I say the word vector, but let's talk what exactly is a vector. You know how sometimes you have these words like somebody's going to be driving 60 miles per hour? Well, that's a magnitude. It's got like a force to it. But as soon as you start saying, I'm driving 60 miles per hour northeast, so you say, okay, I'm going to be driving this magnitude in this specific direction, all of a sudden you've created a vector. What a vector is, it's all about giving a magnitude focused in a specific direction. Okay? And a lot of times, like you can say the wind's blowing from the northeast at 20 miles per hour. Well, 20 miles per hour is the magnitude of this vector, and northeast is the direction of this vector. So by definition, a vector is magnitude in a given direction. Okay? And so what we have talking about right here is basically, we're used to kind of seeing this as almost like a robot's arm, but what it is now is a vector. Okay? Our vectors have an x portion, it has a y portion, and it's taking us to a final position value. Okay, the final position, p, is equal to, and this notation, by the way, up here on the top, when it's just like half of an arrow, it's referring to the vector. So the p vector is made up of an x portion of this vector plus a y portion, so a horizontal portion and a vertical portion. Now, why the whole I and j part? Well, it's because it's considered almost like a unit vector. A unit meaning one, like the unit circle, we had a radius of 1. So if I say I represents 1 unit, however you want to label your units, let's say x was 6, so therefore it's 6 units long. If y was 4, it's 4 units high. So it's breaking it up into the x component times its unit vector, and then the y component times its unit vector. And again, just like what we did with the robotics arm, the x value was almost like the arm length. It was like L times cosine theta, and the y was L times sine theta. Well, in this case, we don't have an arm length, we have a vector, which is p. Alright? Y'all can kind of see the same thing. And again, what used to be the length of the robotics arm we found that by Pythagorean's theorem. Well, the length or the magnitude of vector p is just the sum of the x portion and the y portion squared. Same thing. And again, the angle, since we're looking at a right triangle, if this is the angle right here, well, with respect to the right triangle, we're looking at the opposite over adjacent, so it's going to be the tangent of y over x, and that's going to give us the direction of the magnitude for this vector. And again, so a vector is an engineering quantity which has both magnitude and direction. It's very, very important. Okay, so let's look at this first part right here. We know that the magnitude for the vector is 0.5 meters and the direction is 30 degrees. So we want to almost decompose this vector into its x components and its y components, and then we'll use it in vector notation. Okay, so going up to our formulas and what we can use, we know that p is equal to the square root of px squared plus py squared, and that we also know that theta is equal to the arctangent or the tan inverse of the y portion over the x portion. Okay, so that's stuff that we know. And for further formulas, we know that px is equal to, the x portion is equal to p times cosine theta, and py is equal to p times sine theta. Okay, so like our arm length times the x and arm length times the y. Okay. Well, since in this part we're asking to find px and py, obviously we're going to go with this formula here and this formula here. And then once we find those two, we'll come over here and use theta to help finish this out. Alright, so filling in what we know, then we can say the x portion of this vector is made up of 0.5 times the cosine of 30 degrees. So the x portion is 0.5, and the x value at 30 degrees is the square root of 3 over 2. But because we actually want to get a point, we're going to call this 0.433. Okay? The y portion is going to be 0.5 times the sine of 30 degrees. So it's 0.5 times the y value there at 30, which is a half. So 0.5 times 0.5 is 0.25. Okay? And again, if I wanted to check, let's make sure that if I take the tangent inverse, let's check to see, does 30 degrees equal the tan inverse of, basically, if I did 1/2, if I wanted to write this all in a fraction form, it'd be the square root of 3 over 4 divided by py, a half times a fourth. And if you go through and check that, you'll see that it actually will work out. Okay, so it's always good to look at that. So what we have just found then is that our x value broken down of our vector is 0.433. Our y value broken down is 0.25. Now it says it wants us to write this in vector notation. Well, in vector notation, let me come back up to this so you can see it again. Vector notation is involving your x portion times the unit vector, your y portion times the unit vector. Okay? So our vector in general is going to be 0.433, so our x portion times its unit vector plus 0.25 times the y unit vector portion, and then all of this was in terms of meters. So that right there is our answer. Okay, let's try this again. This problem looks like it has us kind of go in the opposite direction. Now we know the x portion of our vector, we know the y portion of our vector, and this time we're going to go back and now find the actual magnitude and direction of it. Okay, so using our formulas, we know that p is equal to the square root of our x portion. Whoops, I say x portion, why I'm writing it r I have no idea, but our x portion squared plus our y portion squared. Okay, so p is equal to the square root of the square root of 3 over 4 squared plus 1/4 squared. Okay, so keeping on with this, p is equal to the square root of the square root of 3 squared is 3, 4 squared is 16, plus 1/16. So p is equal to the square root of 4 over 16, and all that together, square root of 4 is 2, the square root of 16 is 4, so p is equal to 1/2. Alright, so we got that one done, and it looks like the units here are going to be meters. So there's p, and then we want to find the direction. So the direction is theta, and theta is the tangent inverse of the y portion divided by the x portion. Okay, so theta is equal to tan inverse the y portion, which is 1/4, divided by the square root of 3 over 4. Okay, so theta is equal to tan inverse. Just cleaning this up if I want to, or if you want to, you can put it all in your calculator at one time. Let's just see if it's something we can at least recognize. So 1/4 times the reciprocal of the bottom, so 4 over the square root of 3. It looks like something we might know, actually. The tan inverse of 1 over the square root of 3. And remember, if I rationalize that, that's actually the square root of 3 over 3. That actually does look familiar. Do you remember the coordinate value? Square root of 3 over 2, 1/2. If I asked you to take that y value and divide it by that x value right there, it's going to give you 1 over the square root of 3. And this happens at 30 degrees. Or you could plug that in your calculator, same difference. So it's telling us, though, that our angle here is 30 degrees. So the magnitude is 1/2 of a meter, and then the direction is 30 degrees. So we can say this. I don't know if we want to say, so we can label that maybe the magnitude. Box that up. And then this is the direction. 30 degrees. Okay, let's keep moving on. And this is where you're going to really see the vector thing going on. Okay, a person is pushing a vacuum cleaner with a force of 20 pounds at an angle of 40 degrees relative to the ground. Let's determine the horizontal and vertical components of the force. Okay, so this is your vector because it's got magnitude. You're doing 20 pounds at a specific angle at 40 degrees. So we're definitely talking about a vector here. And to get this started, let's kind of draw ourselves a little picture. And by the way, this is definitely in statics for sure. But imagine, oh, I'm just going to pretend. Here's your vacuum. It's lovely, isn't it? Okay. And here is your arm coming down, applying force. Okay. And it tells us here that the force of 20 pounds, so F is equal to 20, and it says it's going to be done at an angle of 40 degrees relative to the ground. So how we draw this is obviously this is the ground here, or we can always move it up here. This is also the ground, okay? Any kind of horizontal component we can treat as the ground. And so that right there is the 40 degrees we're talking about, okay? So now we need to break this down, this whole vector, into its x and y components. Well, the x component is going to be our force value times cosine of our angle, and our y component of this vector, instead of calling it p, we're just calling it f because we actually have a force that's giving us f. That's all the reason why I'm changing variables here. But it'll be f times sine of theta. Okay, so f of x, f sub x, the x component is going to be 20 because that's my force, my vector force, times the cosine of 40 degrees. And then that gives me an x component of my vector of 15.32. And in this case, pounds, because that's what they're giving us as units. The y portion is going to be 20 times the sine of 40 degrees. So the y portion, by the time I plug this in my calculator, since 40 is just not something that we're common to work with, it's 12.86 in pounds. Now, this is where we have to get really smart though with our whole putting this all together. Is let's really analyze what's happening here. When you push a vacuum, obviously the horizontal distance, you're pushing the vacuum away from you, okay? But is your arm going up? The vertical distance, is your arm going up to push this? Is your arm going down to push it? Well, your arm's going down. So what we need to do is make this y portion negative, just to make the context of this problem actually more accurate. Okay, so as I look at this, obviously the x is going into a positive direction, but because I'm almost pushing down the y component, we need to make that negative. Okay, so to put this then as a final kind of all together in one thing, we can say the position vector. So the position vector is going to be equal to our x component times the unit vector in the x direction plus the y component times the unit vector in the y direction. Okay, so just putting in our information here, then technically our position vector, which they're asking us to find it, even though we've already broken it down into the vertical and horizontal components, we can always get practice doing this. Okay, that's why I'm just doing this right here. So it's 15.32 times the unit vector there. Instead of plus, I'm going to go minus because we're now going down with our vertical movement. And there you go. So there's the big position vector too, in addition to knowing those two pieces of information. All right.